Welcome everybody, I'm Nikolai Parlok, Java developer advocate at Oracle, and this talk is going to be you, me, and pattern matching in JDK 17 and beyond. If you have any questions, leave them in the Q&A section right away, and I'll answer them during the talk. This is proof that I indeed work for Oracle. And now let's go with a sci-fi novel that I recently read. It's called Salvation by Peter F. Hamilton, and I highly recommend you give it a go. It has a couple of seemingly disconnected storylines that cover time between 2050 and 2200, and another storyline that plays far away in space and time. And it takes until like 3/4 of the book until they finally come together and I realize what they all have in common. And this talk is a little bit like that. And as any good sci-fi novel, it requires a certain amount of suspension of disbelief. So if you think something is a bit off, don't worry, it will all work out in the end. So with that said, let's go. The backstory is that we want to compute a simple arithmetic computation. For example, 1 minus 2 plus the absolute of 3 minus 4. That would be 1 minus 2, that's minus 1, and then 3 minus 4 is also minus 1, but the absolute of that is plus 1. So it's minus 1 plus 1, that's 0. Okay, I think we can agree on that. Now, to compute this, we can turn this step by step into a representation that makes more sense. So you can see on the top level it's an addition, right? We add these three terms together, 1, minus 2, and the absolute of this other computation. And then we can go further. We can say, well, that's the negation of 2 in the middle, right? The minus 2. And at the end, that's an absolute of 3 plus minus 4. And then we can turn that into another addition. And then we can turn the minus 4 into another negation. So we get this like nested term here where it's an addition of several terms, and those are in turn their own computations until at the end you come down to a number. And you can represent this in a simple little tree like this one, where we have add on the outside, and then I put a number node in between the actual numbers and the operation above that. So you have add of a number and of negate, and that negate is of a number 2, and so on and so forth. And now it's time to meet our main characters, and those are these 5 types. We have an interface called node, because we represent this tree in nodes. And we have 4 implementations. These are all records, which I'm sure you're familiar with by now. And the record is a number that, contains a number. And it's a negation of another node. So you can see here that it negates the result, for example, of a computation of an addition, or it could negate another number. So the negation node refers to one other node. And likewise, absolute refers to one other node. In the end, we also have an addition node, which just takes a bunch of nodes and it will add all of them up. Okay, so far so good. If we have this tree that I showed you earlier, then this is how you would represent it, right? So you could see that it's a very, very close representation. You will have a new add node, and then you give it 3 children. That would be the number node that takes 1 as a constructor argument, and then also a negate node that takes number. Oh yeah, I should add. This is not the Java lang number type. This is just a number node, right? As you can see here, this number implements node. So this is not the number that you know from the Java packages. This is a specific type that I created here. It should probably be called number node and negate node and absolute node, but that makes everything way too large to fit on the slides. So I went with shorter names. But once again, you can see this correspondence here, right? So you have new add, that's the add on the outside. Then you have new absolute, which contains an add node, and that, adds the number 3 and the negation of the number 4. So there you go. Now this is the complication. Given a node, evaluate it. Given a node, create compute it to a number, to a result. Well, that's easy, right? On the interface node, we just add a method called evaluate that returns along. And then we implement it. I just did it for the 2 nodes here, but you can see how it would be similar for the other ones. So for example, the number record, its evaluation of its value is just, well, that's just the number that was given to it during construction. And the negate node, if it evaluates something, well, it just takes the node that was given during construction and calls evaluate on that. And whatever the result is, it just negates it, right? And then absolute would make a check whether it's larger or smaller than 0. And then add would actually just add these together. So that's easy, and we're done. But wait, we need a crisis here. So, since we're outer space themed, aliens, those are the crises. If you change the node, we annihilate Earth. So we're not allowed to add a method to node. We're not allowed to touch those classes and change them. we need to evaluate them from the outside. And this is the suspension of disbelief part, and we're going to come back to it later. Okay, so that means we need to evaluate the result of this computation without changing the interface. We need to do this from the outside. So just as a flashback, these are the types that we have, right? The interface node, and then number, negate, absolute, and add, which implement this interface. Well, then given a node, what we can always do, we can do like an if-else cast chain, right? So you can say, well, okay, given this node that I need to evaluate, let's see, is an instance of this number node type? If yes, I can cast it to that type and then get the number out. And that surely is the result of the evaluation of a number node. If I have a negate node, well, then I cast it to the negate node, get the node out that it contains that's supposed to negate, and evaluate that one. And then the result of that, I'll just gonna, at this minus here. And for absolute, once again, I make this instance off check, and then I check, then I cast it to absolute, then I get the node out of it that it's referring to, and I evaluate that one. And once that's done, I'm going to look at the result and be like, well, if it's larger than 0, I can return it. Otherwise, I can return the negative. Or you can use math.absolute here, but I want to make it explicit. And if it's an addition node, once again, I have to cast it to the addition node. I get the summons out, which is the property of the addition node, and then I stream those. I map them to long by evaluating each individual one, and then I have a long stream which I can sum over. This is not the important part, right? The details of how exactly to compute this are not that important. The important part is, how do I get there? Well, I make this chain of instance off checks, and wherever I'm true, whichever case is true, then I have to make this cast and then do the appropriate computation. And well, we know that there are only these 4 types at the moment, at least. Like the compiler doesn't, so we have to add a throw new whatever exception at the end. We could return 0, but that's really yucky. So let's throw an exception in case we encounter an unexpected node. So that's not good, right? That's hard to write and it's hard to read. Like this casting is error prone because we tend to start copy pasting stuff, and then you have to change the instance off check, but then you also have to update the cast. So that's kind of error prone. And if we forgot a node, or if we add a new node, then we will only find out at runtime with, in this case, an exception, which is still the better case than returning null and 0 and silently having a weird result there. Because that's not great. So let's start. We're doing our training montage where we're like increasingly getting better and better. Our heroes are getting better. So the first thing I want to introduce you to is a pattern. Specifically type patterns, but the first half of the slide applies to patterns in general. A pattern is always a test or a predicate, some kinds of check that is applied to a target. So you have a target, you have a test and a predicate on that, and then you have pattern variables. Pattern variables are extracted from the target, assuming a certain the predicate or the test evaluated to true. So that's a lot of theory. I show it here on this specific kind of pattern, which is a type pattern. So node is the target. We take node as a variable, as a target. We make this instance off check. That's the test. It could be a number or it might not be a number. Like 2 different outcomes. But if it is, we extract something from this variable. In this case, we get a new variable, which for a type pattern is the exact same instance. No is the same instance as a node, but it's typed as a number. So now we can use an no as a number down here, right? So we don't have to do any additional casts. And these were finalized in Java 16, type patterns that is. And we will see more patterns in the future. One more pattern just later in this presentation, and then there are probably more patterns coming down the line. Okay, so let's use these. So this makes the code a lot easier because it throws out a bunch of parentheses at least. All the casts are gone. So now if we want to evaluate a number node, we check, well, is it a number node? And then we add the name of the variable here. So in this if branch, node was apparently a number. So we have a new variable no that reflects that. That's exactly like node, but it's cast to a number, so we can immediately call methods on it that are specific to the number class. Same with negate, right? We check if it's an instance of negate, and if it is, we pull out the node, evaluate that, and then, turn it to negative. And, we don't have to go through all of these. What's important here compared to without type patterns is that all the casts are gone. We basically replaced them with specifying a new variable name here and then being able to use that one. That's already a big improvement. So writing and reading these kind of chains becomes much easier. And the error-prone part about casting, that one is just gone. So there's no room left for, I copy-pasted this and didn't update something. So that's good. Next step in this evolution is pattern matching in switch. So as a preview feature in Java 17, and I link to what that exactly means down here, but it means that, how to use preview features, that's explained in the linked blog post. But what a preview feature is something that is basically done, but it still sits as a preview in the JDK, so you can give it a try, right? So you can download JDK 17, you can try this feature, and then you can give feedback, and then depending on the feedback, it might still get changed, usually just a tiny bit, maybe not at all, although theoretically it could still be removed entirely, but that's very unlikely. It will likely just be tweaked a bit until it becomes finalized. So preview features are a great way to experiment with new features and maybe write, a day's worth of code against it. But since they could change, I recommend not to spend all the 6 months between two releases. They're just piling code on a preview feature. That's probably not a good idea. But using them a bit to get experience with them and then give feedback on the respective mailing list, that would be a great way to contribute back to the development of the JDK. But be that as it may. So using pattern matching in switch, that's a preview feature in 17. And that works as follows. You write the normal switch as you would be used to, but now you can pass not just numbers and strings and enums. Now you can basically pass whatever you want. So in this case, we give it the note instance. And that means that in this pattern matching vocabulary, this variable here becomes the target of this pattern match. This pattern match. And then where we wrote instance of number before, now we're going to write case number, which is really just another keyword here, but it's still the test. We still test, is note a number? And if it is, we extract the variable no, and then we can use that. And then we need to cover all the other cases as well. So you can probably see how we can apply this. Now it looks like this. We're going to go, switch over the note, and then, if it's a number, do this. This is the result then. And in case it's a negation note, then, pull note out and evaluate it, put the minus sign there, and then return that one. And if it's absolute, you've seen these steps a couple times now. So the computation in here, they're still the same, but the way we approach them is similar. It's different now. Now we don't do this if-else chain anymore. Instead, we just use a specific control structure that tells us and tells the compiler and tells your colleagues, well, it will only be one of these, right? Like it's one of these that I want to evaluate. Let's see which one it is. So that makes reading and writing them even easier. It's more compact without losing important information and just makes it very clear what exactly is supposed to happen. Now, next step. We're now going to use deconstruction patterns. Now, big warning sign here. Deconstruction patterns are not even a preview in Java 18, right? So they're just a candidate to be a preview in Java 18. So they could still be down the road a couple of releases. But I already want to show you what you can do with those. Because what's possible here is to take apart records. So what you can say, like, well, that the record number only has a single number field. And that all means we can construct it with a number and we can have accessors for that number. It also means we can take it apart into just this number. And this is what we're doing here. And if we would say, well, if note is an instance of number, and now I don't give the outer instance a variable name. No. I give a variable name to the first parameter. So I'm going to basically take this apart into its constituent fields. In this case, that would be the long and O. And the same thing I can do in a case. Okay, so this is what that looks like then if we apply this to the situation that we're in. Now we don't say case number and then have to extract that later. We can do that in one go. We can basically elide the entire variable that we don't need. It can say, look, if you want to evaluate a note, we switch over note. In case it's a number, then just the number, that's the long it contains, that will be the result. And the negate, that's the note it contains. We're going to pass that on to the evaluate function. and the same for absolute, and the same for add. So we can immediately take these records apart, and that works because records are transparent, right? They cannot hide state from the outside world. This is a very important reason for why that's the case. So that means we reduce the number of variables and calls we have, with thus the code is overall more simplified. But we're not done yet. We can do something else, and these are guarded patterns. And guarded patterns are also a preview feature in Java 17. If you're confused about the timeline, once again, it's a little bit like The Salvation by Peter F. Hamilton. This talk is basically a book. I'm going to show you the timeline later. But guarded patterns is something that you can already try now in Java 17. And a guarded pattern means that you can add Boolean checks. Right, so in this case, I use a deconstruction pattern on the number by turning it into, by accessing the internal state. But then also I apply a guarded pattern which checks is the number larger than 0. So in this branch, I can use the long variable no, but I already know that it's positive because, it passed this test. And likewise here, I'm like, well, is it negative? And if we enter this branch, then it was apparently negative. And that also means that down here, I know that, the number must be 0. It's not greater 0, it's not smaller 0, so it's 0. Or does long have an NIN? I don't think it does, right? So now we know it's 0. So this way you can apply checks that you would otherwise have to put somewhere into the execution branch, somewhere into the thing that you want to do. You can now pull that out, basically like an if, and put that earlier and put that on the left-hand side of this arrow, making this a tad more readable even. So in this specific case, I have to admit, it's not like we might not end up writing it like this because we end up with a bunch of evaluation. But what I'm using this for is here. So I say, well, look, we switch over the node, and in case it's an absolute node, that means we need to return the absolute value, which is always positive. We pull out the inner node, and then we evaluate that inner node. And if that evaluation is negative, then we return the negative of the evaluation, making it a positive number. Or otherwise, that means if we arrive here, then it couldn't have been negative, then it must have been 0 or larger 0, and then we can just return the result. And it's a bit unfortunate because I have to evaluate once and then twice, or once and then twice. So I always evaluate twice, which is not great here, but just like to show you what you can do with this is you can pull stuff that you would otherwise have to check in the execution branch out into the switch, and thus make it clearer if you read the switch top to bottom what exactly all the cases are that you're treating here. So yeah, so these evaluates checks into this case, which I find very important. Now, there's one more thing that we add, and it's a bit of a plot twist because since the aliens forbade us to touch node, this is strictly speaking going to lead to the annihilation of Earth, but we're just going to hoodwink them, and we're just going to do it anyway. So we're going to do something that is new that was finalized in Java 17, and that is we're going to use a sealed class, in this case a sealed interface. We're going to control inheritance. We're not just going to let everybody implement the node interface. No, only these 4 types are allowed to implement the node interface. No other type can directly implement it. That's right. So that's an important step. Like if you have a class, it can either be final and then nobody can implement it, or you do some constructor package visibility tricks, or usually it's non-final, then everybody can implement it. And with the interface, you don't have any option usually. Like an interface, everybody can implement a public interface. But if you seal it, then that's no longer the case. You're telling your colleagues and the compiler that only these implementations will ever exist. And that's great because we can make use of that here. Now it's the same code as before, but the default branch is gone. So that means that not only did I save a line of code, which is not important at all, what is important here is that the compiler understands that this interface can only have these 4 implementations, and then it understands that this switch is complete. So it will be happy without having a default branch. And that means if you add another implementation, if you in the end come out and do add another kind of node implementation, then you will get a compile error. So what used to be a runtime error with regular switch or with if-else chains can now become a compile time error. And that's huge because it makes these kind of switches maintainable. You can now decide, and you can now make sure that if you add additional types, you will get compile errors wherever you do these kind of switches, which is great because then you can use, then you can at compile time fix all of them, find all the places that you need to update, do that, and then move on. So this is, by the way, oh yeah, I forgot to say that. This is the final form. This is like, this is the end of the training montage. This is the result that was earlier in if-else chain. Okay, about the timeline, I promise you I want to, clear that a little bit up. Java 16 finalized type patterns. Java 17 finalized sealed classes. In Java 17, you can use patterns and switch, and you also have these guarded patterns, but those are both in preview, in their first preview too. So that's likely that it's going to be like, I don't know, like a release or two before they're finalized. And then in some future version of Java, like maybe crossing fingers in 18, we can get deconstruction patterns as a preview. So once again, those will also take a little bit longer until that's finalized. And those are all the features that I just showed you. But I left a bunch of plot holes. There's so much more we could talk about here and go in depth on pattern variable scope. What it means that a pattern label is dominant or that it's complete. How null handling works in Switch. That's kind of important now. That changed a few things there as well. What are the rules for sealed types? Because you cannot just write sealed interface permits, whatever. There are some rules that you have to abide by. And you can also not just deconstruct records, but also deconstruct arrays. So there's a lot more that we can go into, and I'll give you a bunch of links at the end of the talk that you can check out if you're interested to learn more. Okay, but the happy end here is that we start with the if-else chain, which was hard to read and write, was very error-prone due to this repeated casting, and was really hard to maintain because like the best thing you can do is get a runtime error when I add a new implementation, and that's not great. If you compare this to pattern matching, then this is much easier to read and write. Admittedly, it might take some time to get used to the syntax, right? Just like with lambdas and streams, it's not immediately like, oh yeah, I know what that means. It will take a bit of time, but it uses the well-established switch. It uses case. It uses things that look similar to constructors, so they make it reasonable to understand how things are taken apart during deconstruction. So once you get used to them, it's really easy to read them. You get safe casting, you get easy deconstruction out of the box, so you don't have to nest like, okay, get that thing and then apply that check, and if that's the case, so you don't have to have like a bunch of if-elses on the right-hand side of this branch. You can just put all of that very cleanly into one place where they're all checked. And in the end, if you also use sealed types, you get compiler support for expanding type hierarchy if you want, right? You can still use a default branch, you can still say at this point it doesn't matter when they're new types. But at use side, you can opt into, well, do I want to have a completeness check by the compiler here, or do I just slap on a default branch and it will just work? Okay, so suspension of disbelief over. Now let's discuss when you should use this. So specifically, should we have added evaluate this way? Probably not. I mean, this is a structured type hierarchy that is there to compute a simple arithmetic computation, right? So in that case, like evaluation is probably the most important thing it does. It should probably be on that interface node. Like leaving the aliens aside for a moment, that's where it should have gone. But maybe that's not the only part. Maybe this is like an essential part of your application. What if, for example, you have like huge computations and you need to estimate their resource usage before executing them? Think like, like what databases do before they run a query. Maybe you need have a computation strategy that you need to compute. Maybe, maybe you're running Wolfram Beta or something and you want to invoice your user for the computation that you just did for them. Maybe you want to pretty print. There's actually an example that I link here that I think shows very well how this using this external approach improves an API. And maybe you want to pretty print this computation, but you don't want to put that pretty printing code like into all the nodes. Or even more, maybe you want to draw it on a canvas. And then, maybe you want to draw like a tree representation of it. And I think it becomes obvious that resource estimation, invoicing, drawing on canvas, these are very, very diverse requirements that should absolutely not collide all in the same types. You would have like a type that basically has to know the entire rest of the system because it needs to know all these types like strategy and invoice and, canvas. So that's not great. So a central abstraction can be overburdened with these requirements. And in those cases, you would usually use the visitor pattern, because separating a type hierarchy from its operations, that's what the visitor pattern is there for. But I hope I show you by these aliens threatening to annihilate Earth that not all visitors are friendly. And my personal opinion is that if you use pattern matching specifically over sealed types, you will often achieve the same result with much simpler code without the indirection. And once again, my personal opinion is visitor pattern should be like the third in line. First one is trying to put the method on the type. Second one would, in the future, probably be pattern matching over sealed types. Third one is visitor pattern. Once again, not everybody agrees, but that's my opinion. That's not the only place where you can use this. The edge of space is also always interesting to explore. When you're parsing outside data, you often get very general types, for example, something like JSON node. And then you can use pattern matching as well to tease the data apart and figure out, oh, what kind of JSON node is this? Oh, this is a string. Okay, I know how to handle that. So in that case, it's also very much more straightforward to read and write the code that teases these very general data types apart that often happen at the border of at the boundary of your application to the outside world, where you get in data from the outside world. So as a conclusion, as I just alluded to, polymorphism definitely remains the default approach to adding new operations to types, right? The examples usually show cases where you would think like, why don't I have just a method on the type? And that's usually the right answer. That's what you would do in real life code. Just, for presentation purposes, we pick those examples, but it should still be the default way to implement these operations. But where that's not ideal, or you have very general types, there you should consider pattern matching and sealed types that work together really, really well. And together they make it easy and safe to branch the computation based on some type and some other properties. Okay, we also have some sequels here. I linked to a bunch of blog posts, a great Inside Java podcast with pattern matching for Switch with Gavin Bierman, who's been working on this. That's a great listen. And then I did a Inside Java newscast. And if you want to go deeper, my colleague Jose Pomar did 2 Jep cafes, one on sealed classes and one on switch expressions that touch on related topics. And if you want to find me, I'm NipafX on Twitter. I'm nipafx.dev is my website. I'm nipafx everywhere. Check out inside.java. That's also a great resource. And I think I'm out of time.